Hello everybody, and welcome to the SHARCNET seminar. We'll be talking today about the visualization systems, which is a part of, or the SHARCNET Desktop as we call them sometimes, a part of SHARCNET you're probably not aware of. Now, one of the questions is, why a desktop? Basically, this is to catch a class of jobs that we can't do easily on the cluster. So there's sort of two classes of jobs that people run into. There's the non-interactive, longer running jobs. So if they're non-interactive, you know, there's no sort of graphical thing. They load their input, calculate something, and write it out. You launch those traditionally from the command line. And then you don't really care when they run because you don't have to interact with them. So they work in well with our cluster environment, which you all know. You submit jobs to the queue. When resources come available, it runs it, and you go get the results back. So run later at the batch scheduling. But an interactive job does not fit well in that because the human does not want to wait for resources to become available. So generally these are jobs that are graphical. And you need them to run immediately so you can interact with them. Traditional cases where you would actually see them are pre and post processing. So you have your data, you want to visualize it, you want to generate graphs, you want to look at it. Another typical example is when you're doing development, so you're working on your code. You know, you need to try things out, and you don't really have these delays. Now, you can use your own computer for this, but sometimes, depending on your institution, you may or may not be able to install stuff under it. You may or may not be a person who's very technical savvy. And then, not only that, usually your data is on SHARCNET, so you have to transfer it on and off. Wouldn't it be nice if you could just also do this on SHARCNET? So this, of course, occurred to people quite a while back. And so I think as early as 2007 to 2008, SHARCNET bought several high-quality desktop machines and installed them at several of the institutions for local staff and students to use. So these were installed into various rooms on campus. Here at Western, we had them in the Western Science Center and various other universities. So the machines were two-socket, two-core AMD Optrons. They had 500 gigabytes of local storage. That was a RAID 0 configuration. 8 gigabytes of RAM and a blazing fast Quadro FX 4500. So that dates back to the pre-CUDA days. And these 24-inch monitors, and some of them had high-res 24-inch monitors and up to 3. They were really nice systems. They didn't see much use, though, as it turned out, because of the whole problem of people not knowing about them, having to come down and get rooms to them and access to rooms. And so it was a good idea, but it didn't really pan out that well. Especially at this point in time, too, people, you know, carrying around their own personal laptops and such were really starting to take off. And the price of the big monitors, which was a big part of it, were plummeted shortly thereafter, so people were able to, you know, pick up a 24-inch monitor for themselves. Anyway, so they were installed with CentOS 5, which was kind of at the time, SHARCNET was running Red Hat Enterprise Linux 4 or 5 mix, so that was common. I believe they were divorced from the SHARCNET system, so you know, you had to have an account on it. It was not your user account, and you didn't have access to the files. So over their lifetime, we switched them to Fedora 10. We quickly found that lots of the software we wanted to run required newer libraries than was available in CentOS 6. And then we upgraded them to Fedora 13. We integrated them with the SHARCNET accounts, so you could use your SHARCNET account to log in. And you set up a SSH fuse system, so you could get access to your files on it. As I said, there wasn't much local access, so there was no machine NX added for remote access, and of course you could secure shell into them. And some of them were on the internal SHARCNET network, our SHARCNET network, and some of them were off on a campus network. The campus network didn't turn out very well because, you know, campus networks, They can be pretty oversubscribed, and also we had various security concerns too, because if a person can come and access this machine, if you're technical savvy at all, you can pop the lid off it and reboot it and take over and install password sniffers or pull the hard drive and look at the data. So there was a bunch of issues, but it was a sort of a first attempt. So around 2011, 2012, we upgraded to a newer set of machines. So those machines were starting to get a little long in the tooth. These were 2-socket, 4-core Intel Xeon for the most part. There was also some 6-core Intel Xeon. They had moved the storage up to 1.5 terabytes, 48 gigs of RAM, and then a newer NVIDIA card, the Quadro FX 4800 or the AMD FirePro V900, and of course 24-inch monitors. Again, so these machines provided, we were seeing demand for large memory jobs in particular, lots of the mesh generation and stuff before people wanted to run Fluent. So people were able to run stuff on them that they couldn't get done on the cluster. If it didn't fit well into the cluster environment, we'd push them over to these machines. So these were installed with Fedora 13, and then this was later upgraded to Fedora 17. We were trying to hit every other Fedora release, but we pretty much missed every time, and so we went up by steps of 3 instead. We solved various bugs. There was a notorious file system lockup bug that was caused by a loop with SSH fuse in the kernel that would require rebooting the machine, so that was not so great. Various administrative improvements. We moved away from No Machines NX, which was a commercial product, and we just had the free license. So I think it was limited to like 3 connections or something to VNC. We got virtual GL working on the machines, which meant if you had remote access, now you could get accelerated OpenGL calls. So heavy graphics lifting applications were actually fast. And then finally, near the end of this period, we integrated it with our website. So No VNC is a HTML5 VNC viewer, so you could use that to access the machines directly from the website. You wouldn't even have to install any software on your machine. So by this time, our setup was actually getting pretty nice, if possibly not well known still amongst our general users. I mean, that's part of why we have this talk here. But still, we wanted more. In particular, we were having these machines were a pain because they were located in various rooms, and the power would go out or somebody would turn it off, or you go and reboot it and it wouldn't come back up for some reason, and then you had to walk across campus, or you have to phone whoever's at the local campus. We had one down in Fanshawe, which meant you had to drive across town to get to it. So that was quite not very ideal. And also, we have observed that pretty much nobody used them in person. We were starting to get some reasonable use remotely, but there wasn't much use in person. So we thought, what are we doing with all these workstations all over the place? Let's put them in a server room. This will solve our security problems. It's our server room. We'll have access to it. We can get a server class machine that lets us have remote console. And the other problem we were having was keeping our image consistent, because we'd roll out a constant image, and then they would slowly accumulate local tweaks. Someone would install some software on one of them, and it wouldn't be installed on the other ones, possibly because one of them was down. So we were thinking about these things. And then the other problem we had ran into, which I'll get into more later, was we had a real tension between commercial and open source software. Commercial software generally wanting the Red Hat Enterprise Linux, and the open source software generally wanting the latest Fedora Ubuntu style. So ideally we wanted to run both, but we didn't want to split our machines in half and have half of them CentOS and half of them Fedora, because invariably one of them will become used more than the other, and then you'll be wanting to move machines over. Anyways. So this brings us up to 2014. In 2014, we bought a server class virtual container. It's located in the machine room here at Western. It's a 8-core Intel Xeon E5. It has 204, well, it's actually got nearly 500 gigs of SSD, except for it's RAID 1 now, so there's redundancy there, so it's only 230. 64 gigabytes of RAM. We put in the new NVIDIA K1 grids. So that's 4 GPUs per card, so that's 8 GPUs in the machine. They're not particularly powerful GPUs, they don't have a lot of cores, but we were aiming these machines at more graphical applications. Although some of the 48 gigabytes, we had been doing some testing, putting in newer NVIDIA cards for people to do CUDA programming. So I'll just mention that right now. This machine's not particularly suitable for CUDA. It's a Maxwell card. No, it's a Kepler-based card, but it doesn't have a lot of cores. But it is great for doing some graphical work. Now, being located right in our machine room, we put in a 10G card with a direct uplink into the SHARCNET network, so it has as good of access to the file systems as the clusters do. And finally, it has the IPMI, which is, I forget what the acronym stands for, but that means we have remote power, remote console, so we can totally manage it from our offices, which is absolutely fabulous. So this was installed with Fedora 20, and around this time, Linux has been slowly maturing their container solution, so that's like a lightweight virtual machine. So we installed that, the LXC, and then this enabled us to actually run other distributions inside it. So currently we have installed the Fedora 20 and the CentOS 6, which solved the problem of the tension I was talking about. And being in our machine room, we dropped the SSH fuse, which was slowing down the disk access because it has to do encryption and decryption. And now it's a direct mount. Now at this point, it's still an NFS because the Fedora 20 is a Lustre 2 client. So once we're finished upgrading all our machines to Lustre 2 client, we'll have direct Lustre mount, which is as good as the clusters. And then with various administrative improvements, including the ability to do rolling upgrade, which is really nice. So we can now leave the previous version running while we roll out a new version. Before, if we did a major upgrade, we might have to ask everybody to please log out, and then we can do our upgrade and then tell them you can log in again. So this way here, people remain connected to the one they connected to, and new people automatically get connected to our newer version. And plus, we have the older version, so we can do rollbacks. So it's quite a bit of an improvement on the administrative side. All right. So now a little more about this tension I was talking about. So we have this tension between what you call stable/commercial versus unstable/open source, and stable just meaning changing versus not changing, not buggy versus not buggy. So Red Hat Enterprise, Linux, CentOS being the 3B version of that, it's infrequently updated and released, so they have a long release cycle. So it's the same stuff for a long time. Of course, the commercial guys like this because they can build their package and then they don't have to build it again for a while. So it's good for commercial, good for binary software because the libraries that those software depend on are not changing, so they just build it once. It's bad for open source compiled software because, I mean, it's fine for the first half year or year, but pretty soon, you know, it's got libjpeg version 7 and your open source software needs libjpeg version 9, so you have to recompile libjpeg and, libjpeg needs CMake 2.9 and it's got CMake 2.7, so you have to recompile CMake and, CMake needs GCC, you know, and it just becomes a real nightmare in a hurry. So not so good for open source. So Fedora being you have all these, you install the latest version of Fedora, you have all these latest libraries, so you can just compile your utilities. In fact, most of them have the latest version. So it's just a simple yum install. So frequently updated, frequently released. Good for open source compiled programs, got the latest version of all the libraries. You have the latest version of most packages already packaged for you, so it's just a simple install. But of course, it's bad for commercial binary software because the libraries they require are the previous version. So as I said, we needed both. So our solution was virtualization. So now we can relatively easily run whatever Linux distribution works best. And currently, we've got the Fedora 20 and the CentOS 6. We'll be adding Fedora 21 when it comes out. So we'll just keep on rolling up, and with the virtualization, we don't have to shut down the Fedora 20 when we add in the Fedora 21. So you can sort of see where we're going. We could potentially throw in Ubuntu and Debian as well. Anyway, so yeah, now where are we? So the 8 gigabyte machines are retired. They were getting pretty long in the tooth. The 48 gigabyte desktops are running the last non-virtualized release of our stack, so that's the Fedora 20. The 64 gigabyte server is running our new virtualized release, and that currently it has a CentOS 6 and Fedora 20 it's serving. Now the software, we have the cluster and commercial packages on CentOS, on our CentOS 6 image, on the VDI, on our virtualized system. So I mean, that's the other nice thing about the CentOS 6, because that matches exactly what we have on the clusters. So anything compiled on the clusters should run on that. I mean, leaving aside hardware differences. And anything on it should run on the clusters too. So you should have access to, or I mean, we can certainly give you access to any of the SHARCNET stack, standard cluster stack on that machine with it, and then you get the desktop interface. And then the recent open source packages we've put on the Fedora 20 image. So this is the ParaView, the Visit, the Scilab, and all these good things. And we're happy to install additional distribution packages. You know, if it's just a matter of us doing a yum install, just drop us an email and we can do that if there's something we've missed that you'd like. Okay, so now how to connect. I'll be going through this, the second half of this presentation. It's going to be a demo. So the first thing you need to know is the sessions only last as long as the connection, so they're not persistent. That was one thing. The original NX system did support persistent connections, so when we went to the VNC, that was lost. We're hoping to bring that back at some point, so I'll have some more details about that later. Now there is a bit of a detail when you're switching between like a Fedora 20 and a CentOS 6. And that is the CentOS 6 will be running the old version of the software, and so it'll have the old version style of configuration files, and the Fedora 20 will be running the new version, and so it'll have the new version of the configuration file. So if, say, you run the CentOS 6 one, and then you run the Fedora 20, it upgrades all the config files, and then you go back to CentOS 6, and CentOS 6 is horribly confused by the new format. So it's a good idea to blow away your .config, .local, and .cache directories before switching your distributions, and then you just get reset to the default. So that's a key thing to know. Otherwise, you'll wind up with a very screwed up looking desktop. So now we have two ways of connecting. We've got the web browser, so it's more convenient. You don't have to install any software. It's a little slower, not really though. Probably the most annoying thing is you have some additional screen decoration, which takes away a bit from your screen real estate, and it eats some of your keystrokes. So like Alt-Tab, your computer picks up instead of the remote computer. Now the native client, oh yeah, and so any recent browser, HTML5, and then you connect. There's some blue icons on our system page. You can click on that, it'll automatically start that up. I'll show that. So the native client, you have to install some software on your machine. That's not a big deal though. It's faster, and generally it does a really good job, or at least the Linux version, which is the one I do, at capturing all of your keystrokes and passing them through to the remote desktop. So what sort of native client? You need a VNC client, and it has to support the X509 vEncrypt protocol. We recommend Tiger VNC, and there's directions on how to get that on our website. I'll be showing that as well. And then you connect to the machine.user.sharcnet.ca, and don't miss this .user bit. That's important. It's required for for technical reasons, basically, for our X509 certificate. So now, what software do we have on these machines? We've got a whole bunch of software. So some of the general purpose visualization software, we have the ParaView and Visit packages. I'll be showing the ParaView one of those here later. Now for discipline specific, we have the XCRYSTIN, which is a crystalline molecular structure viewing, VMD, which is the molecular visualization package, YT, which is the volumetric one commonly used in astrophysics. And then we've installed several environments for working with packages people like to use. So Scilab, which is like the MATLAB, quite a bit like the MATLAB environment. So there's Scilab and Octave are sort of two spins on the open source spins on the MATLAB. There's RStudio, which is R, which is the open source version of S+, basically. So that's very nice. There's the IPython, the interactive Python. I was hoping to demo that, but unfortunately I didn't have enough speed to get up on that, enough time. And then there's Eclipse, which is the integrated development environment. Started out with Java and it's basically expanded to everything. So your C, C++, it's got GDB integrated into it nicely. So if you're used to using like Virtual Studio or something, you'll quite like Eclipse. So now where are we going in the future with this here? So we're going to be converting our 48 gigabyte machines into virtualized ones as well. So first of all, we're collecting them out of their current locations and moving them into our machine room. We'll probably be done in early December. And then we'll re-image them to our virtual image. So they support virtualization after we finish some work we're working on the imaging infrastructure. So I mentioned earlier that it's a pain trying to keep everything in sync. So we've got some stuff we're doing to make that a bit easier on ourselves. And then in the future, we want to add support for persistent per-user virtualized sessions with the idea that the session will last for some fixed time after you last connect. So as long as you keep reconnecting, your session remains. We're some fixed time will probably be a couple days. And then this will solve our problem of people going away and forgetting about it and then running forever on the machine. So I think that's a nice solution. And we've got some further back-end infrastructure work and plan, which won't, you guys won't really notice anything about that, but it'll make our lives quite a bit nicer. All right, so now we're going to move on to actually showing these systems off. So I'm going to just share my desktop here. Okay, so anyway, so yes, so I'm logged in now. So now there's two sort of things that are good to know. The first would be under the Help wiki. If you just search for remote desktop, there's this remote graphical connect. There's the visualization station section. So this is the remote graphical connections wiki page. The visualization station. So then there's the instructions to use the web browser, which basically is go to our systems page. And then to download the client here, there's this Tiger VNC on GitHub link, which if you click on that, takes you over to here. And now you probably don't want the pre-release. Let's just jump down the page a bit here. Yes, so go with the latest, and binaries are available here. So if you just click that link, and you scroll down, so there, that's the one for the Mac, the DMG, and then the EXE, that's the one for Windows, and then finally the Linux is a source tarball. Although on Linux, if you go back to our remote graphical connection page, you will see for Fedora, you should just yum install it, it's available. And Ubuntu Debian, we actually recommend use GVNC Viewer because it's not packaged yet. Tiger VNC isn't, and it's actually quite a bit of work to compile it. And then that's just an apt-get install, and then you have to do a little bit of work with your certificate. And then also there you can use SSVNC, but I wouldn't actually recommend that. So anyway, so that is the full list of sort of native clients. All right, so let us go back now to the website. I'll just get out of this here. Okay, so now on the systems page, on the facilities, because I can click on it. So facility systems. If we scroll down here to the visualization stations, this is our visualization options. So you see these two that are conditions. That just means that this is our newest and we'd like people to try it out more. This is the container one I've been talking about. And then these other ones are the ones that are located at the various sites. These are the ones that in December we'll be bringing back to a machine room, and then eventually making them container images as well. So for this presentation, though, I'm going to use the container image. Okay, so I will just, if I went to the CentOS 6 system, my desktop would be subtly screwed up because I was last into the Fedora 21. So let's just go log into the Fedora 21. So I click on the blue icon there, and then it opens up my connection here. And I'll just make this screen a little bigger so you can see the full thing. There we go, and I have a desktop in my web browser. So use my password and login name. Okay, and this is the XSpice desktop. There's also the we've got the LXD, the 2 Lite desktops available. There is an icon right up here that you could click on, and it would let you pick which desktop it pops up. So now this is the visualization station. I've logged in. You can see it. Here's my files. Well, I mean, since I got a graphical viewer now, I can, use a graphical viewer, and the work directories and all that stuff are here. So there's my work directory. Now the Scratch directories, of course, because this machine here has access to the cluster Scratch directory. So it's set up the same as the DTN system, which is the data transfer node, which is the one we recommend you use to transfer data because it doesn't have a CPU time limit. If you transfer data to clusters, directly to the clusters, if you exceed 1 hour of CPU time, your transfer will be killed. So it mounts several of the clusters' Scratch directories. Currently missing are, let me see, I think it's Orca and Redfin, is it? One of these won't actually have anything inside it. Yes. And that's because we can only directly Lustre mount that, so that's still waiting until we finish our upgrades on our Lustre system. But the other ones, oh, yeah, that's still on the file. Yeah. So there, you can just go in and under your subject. I don't have anything in any of my Scratch directories, so there isn't really that much to show there. All right. Now, one thing to be aware of is the shell environment does not persist across Windows. So, well, there isn't any modules on this system. But if I was on the CentOS 6 one and I loaded a module in this window, and then I open up another window, it gets another copy of the environment that does not have, it's reset to the default. So I'd have to load the module again for each window that I want to use the module. So that's just a detail to be aware of. Okay, so let's have a look at some of these packages I was talking about earlier. So I thought I would start off by showing some of the integrated environments because I think they're very nice. So let's go application menus, development, education, Scilab. So Scilab is the sort of MATLAB-like. Oh. All right. So let's just do, I mean, if you're familiar with MATLAB at all, so I'm going to just make a vector here from 0 going up in steps to 0.1 to 2 pi and transpose it so it's a column vector. So there we go. And then I'll just plot x and say the sine of x. Very nice, right? If you suffered through doing plots in things like for GNU plot and stuff, you'll appreciate having an environment. So there's an example, a basic example. Let's have a look at plot 2D 3 x sine x. So some of the plot functionality available here. So now we're plotting it as a series of impulses, showing because it's actually discrete values, right? Say we want to crank this up a bit more, so make a matrix out of this, because remember these were column vectors, sine of, so we'll do 2x, sine of 3x, times 2 times x, sorry about that. There you are. You can see it's colored them all. course, you have all the help. Help, say, plot 2, 3. Hey, look, there's my example. I just ripped off a whole bunch of examples from the help. Anyway, so let's give you a little more sophisticated plot here to give you some of the ideas. So we're going to do a black diagram with a Nicholas chart. Oops, that wasn't what I wanted. So we're going to make a polynomial. So basically we're going to work with some symbolic expressions. So we're going to have a plant system here, which is a linear system. C, and here's the transfer function of s plus 1 times s plus 10. So if you're familiar at all with these sort of engineering things, this would just be the Laplace transform of the impulse response. And you use it for controlling feedback in particular. So here's the transfer function. So it's a polynomial in the S space. And then we're going to look at a proportional integrated differential controller. So that's a sort of standard controller they would throw in a plant to handle the feedback. So characterize it by these variables here. So the PID will also be a system transfer function in C of 1 divided by 2 psi times tau times S times 1 plus 2. So again, it's just a simple transfer function. Tau times S. Tau squared times S squared. All right. So we'll just clear our plots. Plot. There we go. And then we'll do the black plot of the plant and the plant times the PID. So we're working in the S space, so essentially we're convolving it, we're throwing it in there. Okay, so and then we'll label them plant and PID. Correct. Semicolon. There we go. Now, of course, I don't have all tab because this isn't a browser, so I'll just have to move this aside so you can see the graphics window. Oh, there! A fancy plot here showing the original plant response, and then with the PID on this diagram that gives the magnitude of the response versus the phase angle. So that's the sort of stuff you'd need to know in order to design your control circuit, tweak your parameters to make sure you have a stable feedback system. So we can turn that up a little fancier here. So we'll just get a hold of the axes and then the legend. And then we will put the legend down in the lower right. So look over our graphics here. So we just pop that down into the corner there. And then let's throw in the full background so you can actually see. So we'll put in the Nichols chart colors. Gray. So there, that's a fairly fancy chart there that actually shows the relative values in the background. I guess these circles have something to do with the stability. Anyway, so there, that's Scilab for you. Quite sophisticated graphics capabilities, very nice sort of display. You can see all my variables and stuff here, command history, I can load my files, very much sort of like the MATLAB environment if you're familiar with it. So I definitely recommend checking that out to, you know, if you got some values you want to graph, some plots to do, very extensive help installed in it. So, okay, well, let's move away from Scilab now. So we'll close that down. The next package I wanted to show you is our studio. Fire that up. So this is the S+. This is a package that's used quite frequently in statistics. Very well known for its powerful plotting abilities. So let's install here, install package. So ggplot2, which is the sort of latest craze that everybody is. Oops, sorry, it's package.install. I can't remember what it's goes, so I just find what the correct command. Install.packages. So question just did a search here. Install.packages. ggplot2. So this is actually quite a nice interface here. You can see it connects automatically to the upstream website, downloads all the necessary components, and compiles them up for me. So just let that work away in the background. Let me see if there's something more I can tell you. Yes, okay. So here's, while that's going, let's talk about the desktop side. So you can see we have a default desktop side, and if you want it to be bigger or smaller for your screen here, if you go under the settings, there's a display setting. And here you can actually pick the resolution. So let's drop down to 800 by 600. There you can see it's shrunk it down, so it's not as go back with the previous. So that way you can come up with something that's fairly close to your native screen resolution. And I see this background did a very nice job of redrawing itself. Oh well. So that's a good thing to know, how to change your desktop. I'm going to just set this back here, so hopefully it'll. No, I guess I'm going to. Okay. Anyway, so ggplot2 has been installed. So let's use it now. Library ggplot2. So that just installed that into my home directory. Okay. Now there's the R packages commonly come with sample data sets, and this one is no exception. So it has this NT cars. So I'm just going to grab the global NT cars and assign it to a local variable. Here we are. Let's make this full screen. It seems to have thought that that was since I changed my resolution. Okay, I'm just going to put it back, and then I will drag it bigger. Okay, so this data set here, if I click on it, you can see it So this is a collection of cars and their miles per gallon and various statistics about them. So we're going to just make some minor changes to it there. So we're going to change the gear information to be factor-based, which basically changes it to an enumerated type. Empty cars. Dollar gear. So I'm just assigning it to itself with the change that I'm changing it into 3 levels, so 3 different enumerated types, and I'm going to give them some labels for graphing. So we'll call it 3 gears, 4 gears, 5 gears. Alright, so, and then I'm going to do the same for the automatic transmission, which is currently just a number. So really, that's 0 would be no automatic transmission, 1 would be automatic transmission. So we'll call that automatic versus, actually that sort of seems backwards. Oh, and I almost goofed that up here. I've got to put automatic transmission on the side. Okay, sorry, I'm going to have to do that again. So it was automatic, and probably, so we're going to assign automatic to automatic. Levels are 0 and 1. The labels will be manual versus auto. All right, and then finally will be the cylinders. So cylinders to assign to the cylinders. And again, there's 4 levels of cylinders, 4, 6, and 8. And we'll change the labels to be 4-cylinder, 5-cylinder, and 8-cylinder. And let me just correct that. I see I put a Y instead of a. All right. So now let's have a look here. I'm going to just do a quick plot, it's called, of data of the MT cars. We're going to do a density plot, density. And we're going to set the fill type, so the fill, the color basically indicate the gear. Set the alpha value, so partially transparent plot. And then we can set some titles. I'll just do it on this first plot, but I'll skip that on later plot. Distribution of gas mileage, right? And on the next label, we'll say miles per gallon. Y label. Okay, so now here's my plot, and you can see miles per gallon over the distribution of cars with 3 gears, 4 gears, or 5 gears. All right, well, you know what? I'm just going to skip that plot, and I'll move on to my last plot I was going to show you in our studio here. So this is actually a pretty amazing plot. So this is going to do some regression, so linear regression of with the formula. So we're going to regress with y as predicted by x. Y if I spell formula right, formula y is x. I'm going to color it by the cylinder. And here you have, so 4-cylinder, 8-cylinder, and then our other one, which I guess was the 5-cylinder. And you can see the points have been plotted, and the linear regression line, they're all sort of broken up into other ones, and some information about the air ranges and the weight versus the miles per gallon. So not too surprising. As the weight goes down, your miles per gallon goes up. As you add more cylinders, your miles per gallon goes down across all the classes. So anyway, some very powerful sort of plots you can do in a hurry there. Let's move on to my last example, which is the sort of general purpose pair view program for doing visualization. We'll just close this down. With our studio, don't save. So applications. So again here under graphics, we have the pair view and the visit viewer. So the pair view viewer, bring this up. So the pair view, as you can see, can import a lot of sort of standard file types. And I had in here the PV directory, yes, the PV data set. So this is the typical standard pair view variable they like to show you. So I'll just show you some very short visualizations. So, oops, that was not actually the data set I wanted. But let's start with this one. This is a time-based data set, actually, of a sort of irregular structure. So this gives you a real example. So let's add some additional information to this here. So we'll turn on some colors. Let's color by ETPS here. We'll rescale that to the actual range, and we'll throw on a scale so you can actually see it. And then let's step forward in time so you can see some of the cool things. So what this actually is here is a structured mesh example. Let's actually rescale that. And you can see it's a solid block being forced down, crushing a can, and we're looking at some sort of information here about the stress or something on the can as it comes down. So pair view, you can deal with time series. You can have very different geometry and values defined on those geometries. Very powerful visualization program. So that was just a quick example. Let's have a look at some more data here. This is the one I had actually meant to load. So I think this is some sort of furnace or something in here. So we'll load in these variables. And we will color it by temperature. So you can see down at the bottom there the temperature is quite warm. Now I can turn on let's switch over to having a wireframe. Here we go. Let's add an isosurface. So we'll make a contour. Let's look for regions of constant temperature, say. Now the temperature ranges from 293 to 913. So let's pick out 400. And we'll color that surface contour. What's my color options here? Okay, let's apply that. There's the region of constant temperature. And we're going to color that by the pressure. So you can see there it's extracted an isosurface inside that volume, the region of constant temperature, and it's put on the outside the pressure. So anyways, I see I'm pretty much out of time. well, I'm actually a little bit over time, so I'm going to end it there, but I hope that's giving you an idea of some of what we have in our visualization stations and where we're going, and some of the powerful software that's available there that you may want to look into to view some of your data. Thanks very much.